welcome to Astronomy and Space. All of this week's news updates have one thing in common, the Milky Way, which is our main theme. The first planet outside our solar system was discovered in 1992. At the present time, a total of 905 extrasolar planets have been discovered around stars within our Milky Way by various methods. Many are hot Jupiters, orbiting close to their parent star, and a small number are large planets orbiting within their star's Goldilocks zone, the region that's not too hot or cold, where alien life is possible to flourish. This week, a new study by the University of Chicago and Northwestern University said that the Milky Way alone could contain 60 billion planets orbiting red dwarf stars that could support life. A red dwarf is a small and relatively cool star on the main sequence, either late K or M spectral type. Red dwarfs range in mass from large planet-sized solar masses, the upper limit for a brown dwarf, to about 50% of the Sun, and have a surface temperature of less than 3,727 degrees centigrade. Red dwarfs are by far the most common type of star in the Milky Way galaxy, at least in the neighbourhood of our Sun, but due to their low luminosity, individual red dwarfs cannot easily be observed. From Earth, not one is visible to the naked eye. Proxima Centauri, the nearest star to the Sun, is a red dwarf, type M5, of magnitude +11, as are 20 of the next nearest. According to some estimates, red dwarfs make up 3/4 of the stars in our galaxy. The researchers based their study, which appeared in the astrophysical journal Letters, on rigorous computer simulations of cloud behaviour on alien planets. This cloud behaviour dramatically expanded the estimated habitable zone of red dwarfs, which are much smaller and fainter than stars like our Sun. Clouds reflect sunlight to cool things off, and they absorb infrared radiation from the surface to make a greenhouse effect. That's part of what keeps the planet warm enough to sustain life. The planets believed capable of supporting life fall into habitable zones where they are of the right temperature to be able to have liquid water on their surfaces, a requirement of life as we know it. As red dwarf stars are slightly cooler and less brighter than our Sun, the planets are usually closer to their star. This brings us to the news from the European Space Agency and their latest space observatory named Gaia, G-A-I-A. It has just passed all of its pre-launch tests in Toulouse and is now en route to the launch site in French Guiana for its flight on top of a Soyuz STB frigate launch vehicle. Gaia is a global space astrometry mission. Its goal is to make the largest and most precise three-dimensional map of our galaxy by surveying an unprecedented number of stars, more than 1,000 million of them. During the course of its mission, Gaia will map all sources brighter than visual magnitude +20. Gaia will operate from the second Lagrange point, L2, of the Sun-Earth system and will be able to observe down to an angular distance of 45 degrees from the Sun. This allows for observations of objects in the asteroid blind spot between the Sun and the Earth, and to discover small bodies orbiting the Sun inside the Earth's orbit, a region that is virtually unobservable from the Earth. Objects that are in more exotic orbits are also potentially discovered by Gaia during observations of the sky regions far from the ecliptic. It is expected that Gaia will also detect several thousand near-Earth objects, which are thought to be comets and asteroids that have been nudged by the gravitational attraction of nearby planets into orbits that allow them to enter the Earth's neighbourhood. Here is Gaia project scientist Timo Prusti.
NASA's Gaia mission will be the first to chart 1,000 million stars, creating a unique vantage point to eventually give us a precise and extensive map of our galaxy, the Milky Way. Using astrometry, the science of measuring the positions of celestial objects, Gaia will conduct a massive census of over 1 billion stars in our galaxy, monitoring each of its target stars about 70 times over a 5-year period. It will chart precisely their positions, distances, movements, and changes in brightness. With its 3 onboard instruments, Gaia is expected to discover hundreds of thousands of new celestial objects.
So the main instrument is the astrometric instrument, which is measuring the positions of stars. The second instrument is a photometer, which is spreading the light of stars into colors, and by interpreting these colors we can deduce the temperatures and even the chemical composition of these objects. And the third instrument is a spectrometer, where we see the lines of these stars, and by interpreting these lines we can see the velocities the objects are moving towards us or away from us. And when we combine all these 3 quantities together, we know where the objects are, how they are moving, and what kind of objects they are.
Gaia's huge stellar census will provide us with the observational data to tackle an enormous range of important problems related to the origin, structure, and evolutionary history of our galaxy. It will do this with incredible precision, building on the principles of ESA's previous astrometry mission, Hipparcos.
Hipparcos was the first astrometric mission of the European Space Agency, which was launched in 1999, so 25 years ago. And Gaia is based on that, but is using a technology which has evolved tremendously in the last 25 years. Hipparcos was able to measure 120,000 stars of our galaxy. Gaia will measure 10,000 times more stars. Hipparcos was measuring at the accuracy of 1 milliarc second, and Gaia will measure with an accuracy of the order of microarc second, which is equivalent to measure the size of a human hair from 1,000 kilometers away.
Gaia's expected scientific harvest is of almost inconceivable extent and implication, but who's going to deal with this huge amount of data?
On an average day, we are going to have 400 million measurements, and in order to make sense all out of this, we have a consortium of 500 astronomers and engineers in Europe who are going to look into this data and make catalogs available for all astronomers to use for their research.
This massive amount of new information gathered by Gaia will impact on many areas of astronomy, from the study of dark matter to the discovery of many thousands of planets in orbit around other stars. But above all, it will give us a glimpse into the way our own universe, the Milky Way, was formed and how it's likely to evolve in the future.
Now on to our main theme. Much of what we know about our galaxy, the Milky Way, comes from observations made through good-sized telescopes over the last 140 years. So let us start from the beginning. On a summer night when the sun has long since set and the stars are shining brilliantly, one of the most wonderful sights in the night sky is the Milky Way. It stretches across the sky, making a band of radiance which catches the eye at once. As Ptolemy, the last great astronomer of classical times, wrote in his Almagest 2,000 years ago, the Milky Way is not a circle, but a zone, which is almost everywhere as white as milk. And this has given it the name it has today. This zone is neither equal nor regular everywhere, but varies as much as in width as in shape of colour, as well as in the number of stars in its parts, and by the diversity of its positions. Also because in some places, as in the constellation of Cygnus, the Swan, it is divided into 2 branches, as is easy to see if we examine it with a little attention. As a description of the Milky Way, seen with the unaided eye, Ptolemy's account could hardly be bettered, but it was not until the winter of 1609-10 that any great advance in astronomical knowledge of the familiar Milky Way could be made. It was then that Galileo first applied a telescope to the skies and discovered that the Milky Way is composed of a vast number of faint stars. These stars give the appearance of being crowded closely together, but in fact nothing could be further from the truth. Galileo and his contemporaries know very little about the shape of our star system. The first reasonably correct picture of how the stars are arranged was not drawn up until the late 18th century, due largely to the work of one man, William Herschel. Herschel was Hanoverian by birth, but spent most of his life in England. Following his discovery of the planet Uranus in 1781, he was able to give up his original profession, that of music teacher and organist, in order to devote his life to astronomy. His main ambition was to solve the secrets of star distribution, and for many years he worked away at the problem, carrying out what he himself called reviews of the heavens. Herschel's telescopes were homemade and were probably the best of their time. The largest was a reflector with a focal length of over 13 meters. Herschel knew that he could not possibly count all the stars visible with his telescopes, so he decided to count the stars in certain selected regions of the sky. He believed that the apparent brightness of a star was a reasonably good measure of its relative distance from us, so that brilliant objects such as Sirius and Rigel were likely to be closer than fainter stars such as Polaris or the 7 members of the familiar Plough. In consequence, the regions of the sky containing the most stars would represent the greatest extensions of the stellar system. During the course of his star gauging, he found that the faint stars became unexpectedly numerous near the Milky Way band. The increase in frequency was greater than for brighter stars. This led him onto a scheme according to which the stars were arranged rather in the manner of 2 plates clapped together by their rims, with the sun lying near the centre of the system. At once the Milky Way appearance could be explained without the need for any actual crowding of the stars. An observer looking along the main plane of the system would naturally see many stars in almost the same line of sight, one behind the other. At right angles to this plane, the sky would be relatively barren. Herschel's final conclusion was that the stellar system is shaped like a cloven grindstone. Many of Herschel's ideas have been confirmed by later research, and his picture of the stellar system is by no means wide of the mark. His main error was in supposing the Sun to occupy a more or less central position. We now know that the actual centre lies at a distance of 25,000 light-years from us, in the direction of the Sagittarius star clouds. Yet Herschel's mistake was both natural and inevitable, since in his day there was no means of determining either the distances or the luminosities of the stars. All that could be said with certainty was that the stars were immensely more remote than our near neighbours such as the Sun, Moon and planets. In 1838, 16 years after Herschel's death, the German astronomer Bessel managed to measure the distance of a dim star in Cygnus. Other determinations followed, and for the first time the majestic scale of the stellar system became known. This in turn led to accurate estimates of the luminosities of the stars, and some of the results were decidedly unexpected. The stars differ so widely in absolute brightness that apparent magnitude is by no means a reliable guide for judging distance, as Herschel had believed. Of course, some apparently brilliant stars are generally near. Alpha Centauri, which shines as the third brightest star in the sky, is little over 4 light-years away. That is to say, its light travelling at 300,000 kilometres per second takes more than 4 years to reach us, while Sirius lies at only 8.5 light-years, and must also be regarded as comparatively near. On the other hand, Rigel in Orion, which comes 7th in order of apparent brightness, may be over 900 light-years away. It appears conspicuous not because it is close, but because it is exceptionally luminous. According to one estimate, it has 50,000 times the candle power of the Sun. Bessel and his contemporaries measured star distances by means of trigonometric parallax. Their results were good, but the method breaks down for all but relatively near stars, since at great distances the parallax shifts become too small to be measured. Gradually, other methods were deployed, but it was not until the present century that a completely unexpected discovery provided the means of spectacular advances in knowledge. This was the period luminosity law of variable stars of short period. Most stars shine so steadily that their luminosity output does not alter perceptibly over many thousands or even millions of years. Fortunately for us, the Sun belongs to this category. There are, however, some stars which fluctuate in brightness, rising to maximum and then fall into minimum before starting to increase once more. Particularly interesting is Delta Cephei, which lies in the northern hemisphere of the sky and never sets in the latitude of Britain. The magnitude changes between 3.7 and 4.3 in a period of 5 days, 9 hours, and the period is absolutely regular, so that it may be determined to within a fraction of a second. The light curve is not entirely smooth, as the increase to maximum is steeper than the subsequent drop, but we can always tell how bright Delta Cephei will be at any particular moment. It is by no means unique. Other stars behave in the same way and are hence termed Cepheid variables. What makes the Cepheid so important is that their period is a measure of their luminosity. The longer the period, the more luminous the star. Hence, a Cepheid of period 5 days, 9 hours will have the same absolute brightness as Delta Cephei itself, while a Cepheid of period 10 days will be considerably more powerful. By studying the period of a Cepheid, we can therefore find out its real luminosity. Its apparent magnitude is easy to measure, and hence its distance may be determined, so that these convenient variables can act as outstanding candles in space. The exact cause of the period luminosity law remains uncertain, but there can be no doubt of its validity. Variables known as RR Lyrae stars, after the prototype object, have shorter periods than classical Cepheids, less than an hour and a half in the case of one star, CY Aquarii, and appear to be of more or less uniform brilliancy, about 90 times that of the Sun. As soon as we observe an RR Lyrae star, we can therefore make a good estimate of its distance. Many such variables are found in the globular clusters, vast spherical groups of stars found here and there in the sky, and they were originally known as cluster Cepheids. The name has now become obsolete, partly because the stars are not true Cepheids, and partly because some of them, including RR Lyrae itself, are not members of globular clusters. The globular clusters are of a vital importance in our studies of the shape of the stellar system or galaxy. The average globular contains perhaps 100,000 stars, many of which are far more luminous than the Sun, yet the clusters appear as faint objects in our skies. Only 3 are bright enough to be seen without a telescope. 2 of these, Omega Centauri and 47 Tucana, lie too far south to rise in Britain. The third, Messier 13, in the summer constellation of Hercules, may be seen on a clear night as a very dim, misty patch, while a telescope of moderate power resolves it into a glorious sphere of stars. Altogether, about 100 globulars are known. Since the globular clusters contain highly luminous stars and yet appear faint, they must be extremely distant. This has been obvious for many years, but until the revelations concerning short-period variables, it had been impossible to find out how far away they really were. The standard candles came to the rescue in no uncertain fashion. As we have seen, globulars contain RR Lyrae variables. The distances of the RR Lyrae variables may be determined because of their uniform luminosities, and hence it was at once possible to judge the distances of the globular clusters in which the variables lie. Omega Centauri has proved to be 22,000 light-years from us, while Messier 13 is 34,000 light-years. Most of the others are more remote still. In the years following the end of the First World War, the American astronomer Harlow Shapley made a determined attack on the whole problem. It had long been known that the globulars are not spread uniformly around the sky. Most of them are in the south, in the region of the summer constellations of Scorpio and Sagittarius, but the distribution appears to be lopsided. Shapley assumed that the globulars form a kind of outer surround to the main star system, and by and by distance determinations he was able to show that this is in fact the case. The mystery of a lopsided distribution was solved. The sum of its family of planets lies well away from the centre of the galaxy, so that we have an unsymmetrical view. Shapley's work led to the first really reliable picture of the scale and shape of our galaxy. The central nucleus lies, as expected, in the direction of the Sagittarius star clouds. The whole system measured approximately 100,000 light-years from end to end, and the Sun is 25,000 light-years from the centre, while the thickness of the system is some 20,000 light-years. Surrounding the main system is the galactic corona, a sort of outer skeleton of globular clusters and individual stars. In this corona, the ratio is roughly 100,000 stars to each globular. It is believed that the total number of stars in the galaxy is about 100 billion. If we could go far out into space and look at the galaxy edge on, we would see a flattened system, with the bulge of the central nucleus showing up very noticeably. If, however, we could look from right angles, it would become clear that the galaxy is a spiral, not unlike a tremendous casting wheel. A spiral shape has been suspected for many years, but an entirely new branch of astronomical research was needed to prove it. Telescopes show us other galaxies lying at distances of many millions of light years. The most conspicuous is Messier 31 in Andromeda. It has been found to lie at 2.2 million light years. Here again, the short period variables, this time the classical Cepheids, provided the means of making a sound estimate. Many of these galaxies are spiral, and there would be nothing surprising in finding our own system to be of the same shape. But while suspicion is one thing, proof is quite another. We cannot see our galaxy from the outside. Indications of spirality were obtained by what are generally regarded as conventional methods. W. Bode, in America, drew attention to the fact that there are two distinct types of stellar populations. The first, population 1, in regions where there is considerable interstellar gas and dust, and where the brighter stars are very white and luminous. The second, population 2, in regions relatively clear of interstellar material, and where the leading members are red supergiants. It appeared that globular clusters and the centres of external galaxies were mainly population 2, while the spiral arms of galaxies were mainly population 1. By plotting the distribution of highly luminous white stars in their own system, inconclusive signs of spiral structure appeared. All this was uncertain, but a solution was to hand. We know that of all interstellar gas, hydrogen is much the more plentiful. It tends to collect into huge clouds and is very cold, with a temperature of perhaps minus 150 degrees centigrade. Naturally, it is very rarefied, and there are, on average, less than 10 atoms per cubic centimetre, which, judged by our everyday standards, is equivalent to what scientists term a vacuum. Needless to say, normal telescopes will not show these hydrogen clouds at all. In 1944, however, the Dutch scientist Van der Holt worked out that hydrogen should be emitting radio energy on a wavelength of 21.1 centimetres. He believed that this energy could be detected by means of radio telescopes, and 6 years later, its prediction was brilliantly confirmed. Our galaxy is made up of perhaps 100 billion stars, of which the Sun is one. The system is arranged in a flattened form, so that the familiar Milky Way effect is nothing more than an effect of perspective. When we look along the main axis of a galaxy, we see many stars in much the same direction. Here on Earth, amateur astronomers like yourself can use a pair of 10 by 50 binoculars to look along the Milky Way and enjoy seeing the numerous star clusters and nebulae on view during summer evenings. Together with stars, the galaxy contains huge gas clouds, nebulae, and clusters of various kinds. There are open or loose clusters, of which the Pleiades group is the best known, and globular clusters such as Messier 13 and Hercules. The Gaia Space Observatory will therefore significantly advance our knowledge of the Milky Way over the next 5 years following its launch. I wonder what new discoveries are waiting for us. That's all we have time for this week. Thank you for watching. When we come back next time, we'll be looking at the highlights of the August night sky. Until then, goodbye for now.